Hello community, so great that you are back. Yes, we have another grand idea in AI research. We use the graph as a universal teacher for LLMs and we optimize LLMs today. Now you know the LLM world is a sub-symbolic world. So we have a vast high-dimensional space defined by billions of numerical tensor weights and biases, and there's no node variable like we have in a graph or in a knowledge graph, no? Instead, all the concepts in a large language model here in a transform architecture are represented as vectors, embeddings, and knowledge is not stored in a database. It is encoded in the geometric relationship exactly between those vectors. Now, you know, LLMs can have beautiful tool calling abilities. Now, this is a traditional program that is symbolic now, and it has variables like node equal 5 and executes hard-coded rules like this one. So you see, with our tools, with our code programs, with our Python environments, with our C++, the logic is explicit and transparent. Yes, of course, if you just add a little bit of memory, you have an agent. But let's come back to the tool. We have with the tool a numerical computer simulation for some theoretical physics experiment in C++. So this tool now calculates here a numerical result given here a specific, astrophysical phenomenon. Now, the way that this calculation was performed in code has an inherent reasoning structure. Somebody thought about how to code it before they started here to calculate here the redshift of galaxies. So you see, in this code hidden is a flow of logic and patterns. And now, when the LLM is pre-trained on a new form of dataset that would integrate these inherent reasoning structures from other languages like a code, it is now forced to map the symbolic world of logic of a C++ onto its own sub-symbolic world. And this is where we can enjoy something beautiful, because we add new reasoning primitives to the reasoning capacity of an LLM, and how we do this simply with a continued pre-training. So, you know, with continued pre-training, we have another problem, né? Highly specialized knowledge, but it lacks transferability. This means even a mathematical exquisite model is not necessarily a better logical reasoning for causal reasoning. And I would have assumed, hey, math and causal reasoning so close. No, in the model, in the AI model, they fail to show the performance. So what we are creating is really narrow intelligence. But how do we foster here a more broader, a more general reasoning ability? And yes, you guessed it, today's new research paper is exactly about how to open up to general reasoning abilities. And they say, if we could identify a class of problems so rich in foundational logic terms, that mastering them would enhance the reasoning capabilities of our large language model across all domains, without relying now on tools. You see, this is a second class of thinking, and they say, tools are great, but we want to integrate this into the reasoning capabilities of an LLM. So what they decided, the authors of today's study, they said we need a diverse set of reasoning skills that go beyond mathematics. We need skills in logical, topological, computational, and enumerative. And I will show you all of this in a minute. So those skills, they say, are now more foundational, more on a deeper level of an understanding than required here some simple traditional mathematical skills or text problem skills for some text bots. So we are going deeper and deeper into the rabbit hole of reasoning and intelligence of a large linguistic language model. Now here, this is one of the drawings here of the beautiful paper, and you have here the topological reasoning clearly in a cluster with a logical reasoning and Hamiltonian path topological sort, maximum click. We're going to talk about this in a second. And you see, if they argue now, if we find here the smallest denominator, if we fall here the core of all of this thinking, of this reasoning, this would now boost here the reasoning performance on all other domains. Topological relationships, yeah, let's talk about it. So this is a brand new idea. They say integrating now the graph problems that we have on a knowledge graph, for example, now into the pre-training process of LLMs. And please notice, this is not supervised fine-tuning. This is not reinforcement learning. We are going back and we go here to the first step, the pre-training of LLMs. The authors say we aim to unlock a powerful tool for enhancing general reasoning abilities across multiple domains. So, CPT, continued pre-training here, is the tool, the methodology that we're going to have a look at. For the green grasshoppers, for all newcomers, what is the difference between a CPT and SFT and on a reinforcement learning? This is it. Continual pre-training. Just think about general knowledge and adapt to new domains, and we do this by large unlabeled text corpora. It's like reading a new set of British encyclopedias here to expand your worldview. Supervised fine-tuning is much more specialized for a specific task. We talk about here training for a downstream task to follow instruction. Normally we do this with labeled examples like a prompt response pair. But this is here very limited. You learn only one new skill. And reinforcement learning, okay, let's go classical 2017 with OpenAI, reinforcement learning from human feedback here. This is just here an alignment and a specific orientation to human values. And you have a teacher providing you the guidance, telling you the model what is good or bad and what is the expected behavior of those models. So we are now going here to the real expansive pre-training, but we are not doing the pre-training. We start with some open source models, some small language model, and we will do a continual pre-training. And this has a lot of operational problems. Let's stick here to the theoretical idea. So continual pre-training, expanding the model's core knowledge base, much like the initial pre-training phase, but we build on something that Microsoft did or Google did or OpenAI did. It's absolute in contrast to supervised fine-tuning, reinforcement learning, GRPO, DPO, whatever you know about shaping here the model's behavior. No? So we are not only trying to improve the mathematical reasoning, but also other forms of complex reasoning in multiple domains, such as algorithmic problem solving and pure logical reasoning without relying here on specific tools like Proofreader, like Lean4 or anything else. So the authors seek here to bridge the gap between the domain-specific pre-training and the development of a more universally capable reasoning model by integrating now complete new reasoning traces here. And they say this would be the holy grail of artificial intelligence. And here we have the study. Those are the authors, Hong Kong University of Science and Technology. A beautiful study. Read it. Published July 23, 2025. Improving LLMs' generalized reasoning abilities by graph problems. We bring now here the complete understanding that we have from graph theory, from mathematical graph theory, that is, if you want a symbolic theory, into a subsymbolic representation of an LLM. Quite a lot of fun. Let's start. We need a training data set. No? And they built here a new data set, a first data set for continued pre-training using here the graph problem reasoning data. They call their training set, you remember in the history we had the pile, now we have a GraphPile and approximately 11 billion tokens. Ne? And if you want to see this, here we have a chain of thought with 2.8 billion token real world graph. Yes, you got it. So we have over 2.6 million samples, and remember, yes, pre-training is, we need a lot. I mean, really a lot of training data. 2.6 million is, okay, on the lower side. It is simple. It is everything that we know. Chain of thought, program of thought, trace of execution. There's nothing specific to it, but let's have a look. Chain of thought. You know it. This is teaching here the LLM the why. So we synthesize here a step-by-step natural linguistic language explanation for solving now graph problems. And you have here a beautiful example here from the literature. So let's test the connectivity. You have here a question and an answer. And now the LLM learns here this graph theoretical problem. And here if you want, the linguistic semantic connectivity here of our tokenized words here in a large language model. It is like learning here another code language, you know. That's not so difficult. We know this works great, although it has massive limitation. So teaches the LLM to develop here and articulate a systematic reasoning process. Not really deep, but it works. The second is here the program of thought. This teaches you the how. This leverages here an LLM to generate precise executable code solution for graph problems. So if you have here your code solution, you just learn this more or less, no? It's just a sequence here of tokens. The third one is a real-world grounding. From our abstract theoretical base, we go now to concrete examples that we use here. Knowledge graph, you might know, or social network if you are into mathematical graph theory, no? The model's ability to reason about complex, real practical scenarios. Like here, find the shortest path here for if you travel from different airports to your particular goal you want to go to Paris. This is all known. This is all there. And finally, this is the new element, if you want, the trace of execution. This is now something that is a little bit more interesting because it's analyzing here the graph algorithmic code and tries to find here the flow. It tries to find here a linear sequence, a flow, in an argumentation why the code was written in a particular way. So the model learns to predict intermediate variable states of the system. So it tries to find your argumentation why the code was written in the way and not in any other different way. So this here, they try here to capture here the dynamics of the reasoning process. A much deeper skill than just a pattern matching. If you go here to GitHub, you just copy and say, this is the pattern. They want to understand the internal dynamic here of this pattern for the reasoning process. This here is really an interesting, innovative element. Let's have a look at a little bit more detailed. I know you want more. Logical reasoning task. Simple. All graph problems are fundamentally based on reasoning derived from the logical rules, thereby they're inherently task of logical reasoning. So, 2 examples. You want to find here, if given a graph, you check if it contains a cycle, this is the definition of a cycle, or other elements. And you apply specific logical rules. No? A cycle exists in a graph if a path from a vertex revisits here the same vertex. So those rules are simple. Topological reasoning tasks are a little bit more challenging. No? Exploring here the relationship between the node and the edges in a graph and making inferences based on those relationships. We have everything that we know about mathematical topology and topological reasoning in the simplest case. Transfer here to a linguistic model, and we have here the example of topological sorting, common neighbors. This is everything that you know. You know here topological sorting here reveals the hierarchical relationship in directed acyclic graphs. Common neighbors highlight local connection between those nodes. More interesting are the enumeration tasks. This is now because sometimes we have to list all possible solutions, all possible configuration, everything that is in a mathematical combinatorial way, a possible theoretical solution to my given query. Everything that goes with a optimization procedure, or everything that is here a search, a guided search, or just a trial and error search. So this is here interesting. If we could analyze this in more detail and have examples, thousands and thousands of examples, to find here enough training data for the LLM to learn this reasoning complexity. And this is, for example, the Hamiltonian path or the maximum click problem. So they did this. They found here 2.6 million examples, and then they said, okay, now we have the training data set. Guess what? We do the continuous pre-training. This is a complexity in itself. I will neglect this step because I will preparing here a video here on this particular topic. How is the best way to continue pre-training your own model? But they went here, and yeah, pre-training is very expensive with very small models. From 2 billion free trainable parameters to 8 billion free trainable parameters, and they did 3 versions of the reasoning model, and now they call their new model with the new training data set in a continued pre-training mode, GraphMind. Here we have it. And at first they look at mathematics. Yeah, so 3 models, we have a Gemma 2 billion, really minimal configuration, a Llama 3 8B, open source, and a Llama 3.18b open source. And you see here for all the mathematical benchmark that you can wish for. And here in the end, we have an average. And you have here the model itself as you get it if you take it here from the shelf. or if you do here discontinued pre-training with the dataset GraphPile, and here you have this and you see there's a huge amount here where really GraphPile outperforms here the normal standard vanilla Llama 3.1 8B. Notice that in the 2B, there are significant jumps sometimes, from 39 to 41, but in 8B, it's almost the same. So the effect in mathematics is not really massive, 3, 4, 5 percentage points. But look at this, look at logic, look at common sense, look at code, look at graph problems. Now we see something moving from 16 to 62, from 33 to 75. Yeah, there are some, I would say, outliers from 3 to 50. But you see, now we have an effect that we say, okay, given the new training dataset, given the new complex learning patterns that the LLM learns now in a continuous pre-training, it shows an effect. Not really on mathematics, but on everything else that is close to mathematics. Logic, common sense, code, graph. So we have a much better performance gain in out-of-domain tasks. Now, they claim here, yeah, this GraphMind outperforms here all the base models, these tiny 2 billion base models, up to 5% in mathematic reasoning and then 22% in other domains. Sounds reasonable. They gave you also then here for graph race, here for classical benchmark. You see, okay, just look at this, no? Gamma 2 at 2 billion is 12.4%. GraphPile is just a little bit better, but let's say 4. If we go now to a more modern Llama 3.1 8B, a little bit bigger, a little bit more modern, you see the increase here is not really there, no? Or here 71.7 to 73.0. There's a little bit sometimes missing, but graph race looks interesting. Look here at this performance jump. So again, you could ask, hey, wait a minute, is this really a general ability for an improved reasoning across all domains? Or is it rather here domains that are rather close here to the original domain that the pre-training data encompassed here? No? If we look at the evaluation detail of the graph reasoning dataset for graph with and graph instruct, you can find that there are some discontinuities. No? Look here at all, yeah, here. This explained to you graph connectivity, flow, shortest path, topological sorting. We went through this, your maximum flow, common Nahiba page rank. Here you have all the benchmarks. You see, sometimes GraphPile is much better, but sometimes here the classical model is better, which is an effect I do not currently understand how this could happen. So there is a not really absolute consistency in this benchmark data. Also here, if you look at this, a Llama 3.1 8B, yeah, you would say, yeah, okay, this looks really good. Yeah? Especially if you go here from 7% to 93%, you would say, okay, here it really shines, no? Here the graph instruct benchmark really shows a significant improvement in the benchmark data. Quite a lot of my viewers ask, hey, can you include here the temperature sensitivity? Great. So here we have a Llama 3 8B. In orange and in green, we have now this super continued pre-trained GraphMind 8B, which is based on a Llama 3 8B. You see here, in general, there is, I would say, some parallel development. However, just look here at this CLRS. CLRS directly tests here the very algorithmic reasoning skill. This is one of the main core reasoning skills that we want to improve here for a general reasoning improvement, the algorithmic part. But if you go at temperature 0.0, yeah, you see, wow, look here. GraphMind here close to 50% compared to, I don't know, 2% from the Llama 3. But the moment you increase the temperature, it completely goes away, this effect. I cannot explain this. You have a lot of numerical data and test data in this report. Have a look at this report, especially the annex. There are tons and tons of numerical data And I've chosen this one to tell you, I think there are still some discontinuities here that for example, I cannot explain where this performance jump is happening. Something seems not to be right yet here for the absolute 100% performance jump. Yeah, CLRS, if you're interested, is of course here by Google. Great. So, what we found, reasoning ability is a very narrowly transferable skill. But there is now a shift from a domain-specific continuous pre-training as a learning methodology, now including here higher complexity reasoning pattern continuous pre-training methods. This is absolutely fascinating. If you think in a transformer layer structure, or if you think the tensor weights, if you think about the complexity of the tensor weights and their hyperplane orientation here in, I don't know, a 1000 dimensional space, they seem to open up new areas, new quarters here of this vector space for higher complexity reasoning patterns, where now here the vector embedding points to this higher complexity objects in a vector space. I will do a specific video on this because I think this is an absolutely fascinating new development. Yeah, and the quest is on to identify other universal curricula to improve here the general reasoning. Maybe we can include more of the formal logic in a linguistic form for the LLMs, or more understanding here in the semantic formulation of physics and the laws of physics to enable here an LLM a better reasoning performance. Or you might say, hey, why? We have the tools. We have everything that we need, no? From C++ to Lean 4 to whatever. We don't need to try to squeeze more of pattern recognition of higher complexity reasoning pattern into the LLM. We have the tools for this. This is the reason why we have agents. They can connect to the world. They can interact with the world. They can use other compute resources. Yes, but the answer is generated by the LLM, so I understand also the other group that says, yeah, great to have tools, great that we have access to all the computer programming and whatever, to PPL. But imagine how good it would be if we could further increase the reasoning capability of the LLM, of the large language model, in the semantic complexity for the reasoning process in general when we get back the results from the tools. So this is an absolute fascinating way to go forward, and I suppose both has its benefits. Yeah, bonus for you. If you made it to this time in the video, just 5 hours ago here, I posted here on my YouTube channel here a simple question. Is this statement true? So the intelligence of an LLM is just the ability to configure higher complexity patterns into learned vector space representation that now offer a complex solution path for advanced graph reasoning. And of course, I did this after I read the paper. And I was just interested how you see this. So after 5 hours in, we have here, you think here, either you have read here as a scientific community already the paper and you know the statement is true because you know the latest AI research. So 65% of you said, yes, I know the paper. I know that you tried to trick us here into an incorrect statement. Great. But you know what? I went to ChatGPT. I didn't log in, nothing. This is here the free version. This is here everybody has access to. No? And I put in the same statement. Interestingly, ChatGPT said, hey, this is false. No? Because, yes. And I said, read it again. It says that the intelligence is the ability to configure high complexity patterns into learned vector space representations. This is a true statement. And if you have seen one of my last videos, you know that small large language models are very sensitive to anchors that are positioned at the end of the statement. And you know what? Suddenly ChatGPT said, hey, you are absolutely right in pointing out that to a significant extent here, intelligent in an M can be understood as my things. Why the statement is true. Now, what a surprise. So whatever you do with this, great, but it came back and said, there's still some nuances here. The second part of my statement, and then I explained the second part of my statement. And then I asked ChatGPT again, so then my statement is true. No? After, if you want, ChatGPT read also this new publication. And ChatGPT came back and said, your refined statement, where I explain what is now the content here of this video, your refined statement is supported by current research and can be considered true. And at this point I thought, ChatGPT, you have no idea what you're talking about. Absolutely no idea. And you can modify and polarize any statement you want from an AI system, independent of the truth, independent of the fact, independent of data. And suddenly, of course, my statement is true and why your statement holds now in hybrid context. And now ChatGPT explained to me why I'm correct. It's kind of funny, but it shows you the current state of AI. And yes, this is another video I would like to make. A lot of my viewers or subscribers hopefully ask me, hey, can you explain the complete state of AI in a 10 minutes video? Yeah, maybe next weekend if I have time. Yeah, it's a challenge. Sounds interesting. If you want to see more, subscribe and I see you in the next video.